Good afternoon to everyone. Myself, Dr. Vishalli, and I'm working as assistant professor in physics in B.Sc Computer Science department at IIMT College of Science and Technology, Greater Noida. So now today I'm going to give a presentation on the topic that is Introduction to Lasers. So first of all, the layout of the presentation. This presentation includes a little introduction to the lasers, then interaction of light with the matter, Einstein's coefficients, components of laser, laser action, types of laser, and finally the characteristics of the laser beam. So a brief introduction about the laser. So laser in this word laser, or the letters are capital, that is laser. It is an acronym for the light amplification by the stimulated emission of radiation. So it means that in this laser, the process is that of the light amplification. We are getting basically the light amplification by the phenomena which is known as a stimulated emission of radiation. So laser stands for the light amplification by the stimulated emission of radiation. So first of all, the first question is, what is the need of the laser? Right, because in ordinary light sources which we use, the light which is coming from the ordinary sources, there is no phase correlation between the light waves which are emitting from the ordinary sources. From the laser, the light which we obtain is highly coherent. It is a very strong, intense, monochromatic, and unidirectional beam of light. So the coherent beam, due to these properties of the laser, it has found many application in various fields. So the principle, as I have told earlier, involved in the laser is this stimulated emission. So this principle is on which the laser is basically based. So we will discuss about the stimulated emission in the further slides. So first of all, this idea was put forward and predicted by Einstein in 1916. And afterwards in 1954, this practically implication of this ideas was made by C.H. Towns and his co-workers. They applied this idea into the microwave radiation, and they called that device as a microwave amplifier, that is masers. Maser meaning microwave amplification by stimulated emission of radiation, meaning they applied this idea of stimulated emission to the microwave region. And soon after, in 1958, Scalo and Town extended this idea to the light, that is in the visible region. And in 1960, first ever laser was built by T.H. Mehman. So after that, the laser has developed as a high technology device, and it is the tool which is used in the different fields. It has found application in almost every field, such as in science, in the industry, in optical communication, be it entertainment, surgery, medicine, etc. So it is a very high-end technology which has been used, and it is we can say that is one of the most recent ones. So before understanding the laser, we need to understand the interaction of light with the matter. So what is light? Light is basically the stream of the photons. Whenever the light is incident on some material, we are saying that the stream of a photon, each carrying the energy is equal to h nu is incident on the material. Now suppose that we have a radiation which is incidenting on a material, and in that material we have the two energy level. You can see here we have this material, we have the two energy levels E1 and E2. The lower energy level is E1 and the upper energy level is E2, and the energy difference between these two levels is h nu. And the photon is basically incidented upon this system. Now when the photons travel through this medium, three type of process can happen. So these processes are absorption, spontaneous emission, or stimulated emission. Whenever a photon passes through the medium, three processes happen. So talking about the first process, that is absorption. So what is there in absorption? We have, suppose a photon is incidenting upon this system. So there will be some atoms which will be lying in the ground state of the system or in the lower energy state. So whenever this light is incident on this system, this atom will absorb this radiation and will go to the higher state, that is the excited state. This process of, or you can say that this transition which atom is making from the lower to the higher state, this is called as the absorption, or we can also call it as the induced absorption. So this process can be expressed as, if we represent this state as a ground state, but it is represented by, suppose, capital A, and the excited state, it is represented by A star. So we can say ground state, by absorbing one photon, has gone to the excited state. So A plus h nu is giving the result A star. So this is the process of absorption in which an atom absorbs certain energy and go to the higher energy level. So this is the first process which can happen. Now, the atom which is lying in the excited state or in the higher energy state, it can't stay here for the longer time, because we know that the higher will be the state, is a state of maximum energy. The energy starts increasing along this direction, and high energy leads to lesser stability. The lower is the energy, more will be the stability. So the atom which is in the excited state, in about 10 to the power minus 8 second, automatically on its own, it will come back, or it will drop back to the ground state. And in this process, one photon will be emitted, which was earlier absorbed in absorption process. Whenever this excited state atom will come to the ground state, it will emit a photon after coming back to the ground state. So this process is called as a spontaneous emission. So we can define the process spontaneous emission as that in this process, the atom decays to the lower energy states, comes to the lower energy state without any external force or any external impedance. On its own, the atom comes to the ground state. So if we have to write this phenomena, we can represent it like A star, which was the excited state initially. After releasing a photon, it comes back to the ground state. So A star is equal to A plus h nu, meaning in this process in which excited state to ground state atom has moved, one photon is being emitted. So this is the process of spontaneous emission. So in spontaneous emission, the photon, it's not like the case we have only this level in the material. There are number of levels and number of excited state atoms within the material. So we have the number of emitted photons, but all these photons are independent of each other. They have no phase relationship between them. All the photons which are emitted from the various atoms, they have no phase relationship between them. So that is why the radiation which will be coming out of the spontaneous emission, that will be a incoherent one, because there will be no phase relationship. And also the rate of fall depends upon the excited state E2 and the ground state E1. So this is a conclusion to draw from the spontaneous emission, that the light beam which is coming out of the spontaneous emission, that will be incoherent one. Now moving to the third process, which is the stimulated or induced emission. Now what happens? Now still again assume a atom is in the excited state. So whenever this atom is in the excited state, before it can make the transition to the ground state on its own, we assume that while the atom being in this state, a photon of energy h nu is incidented upon this system. So before this atom can make a spontaneous transition, this atom may interact with this incident photon, and this incident photon may stimulate this atom to come to the ground state, right? So now the incident photon is interacting with this atom and it is coming to the ground state. This phenomena is called as a stimulated or induced emission, because so we can define the phenomena of forced photon emission by the excited atom due to the action of the external agency. Unlike spontaneous emission, in which the atom has gone to the ground state on its own, here this atom is interacting with some incident photon and then it is moving to the ground state. And in this process, two photons are emitted. These two photons are the photons which are traveling in the same direction. They have the same frequency, they have the same phase and same plane of polarization, etc. And also this process is controllable from outside, because we are sending this because this photon is incident externally formed. It has not gone from the higher state to lower state automatically or on its own. So these are the characteristics of stimulated emission, and we can represent this process like this, that A star plus H nu is equal to A plus 2H nu. So in this process, we are getting the two photons as a result of the stimulated emission. So one important characteristics of the stimulated emission is that, as suppose this is an incident photon and this is a excited atom. Right. So now when this photon will interact with this atom in the excited state A star, it is giving the two photons. Two photons are being emitted in this process. Now there are large number of energy level within the material. So these photons will further interact with two other excited state electrons. As a result, they will undergo stimulated transition and the two more photons will be emitted. So from 2, we are getting the 4 photons. These 4 photons will further interact with 4 more excited atoms, and we have a number of photons emitted, and this process goes on and on. And in this way, avalanche kind of situation is generated, and at the end we are getting the number of photons. So we can say that there is a multiplication of the stimulated photon into an avalanche. So all these photons, as I have told earlier, they are traveling in the same direction. They have the same frequency. They have the same phase. So because of the phase correlation among all these stimulated photons, they form an coherent beam. The light is getting amplified because we have started with the one and we are getting the number of photons in the end. So light is getting, the photons are getting multiplied. So we can say that we have achieved a amplified beam, which is unidirectional and also a coherent beam. So by the process of stimulated emission, we can achieve the amplified unidirectional and coherent beam of light. So for and this is basis of the laser. For the laser, laser meaning the light amplification, meaning to amplify the light, we have to sustain this stimulated emission process. Next is the Einstein's coefficients. Now we have studied all the three processes, that whenever a photon interacts with the material, three kind of process can occur: absorption, spontaneous emission, and stimulated emission. So now we can write the Einstein coefficient, the mathematical expressions for these three phenomena. For that, we will assume that we have the two energy levels, E1 and E2, and we have N1 number of energy, atoms in suppose level E1 and N2 in the higher energy level E2. So whenever the photon will pass through this system, it can be absorbed by any atom which is present in the ground state, and it may be excited to the higher energy state. So the rate of absorption here, it will be proportional to the number of atom which is present in this ground state, as well as on the energy density of the radiation, which is denoted by U. It is a function of nu. This is nu. U is a function of frequency. So this is called as a energy density, energy incidental per unit volume. So we can represent the rate of absorption as RABS. This is the rate of absorption. It is proportional to N1 number of atom present in this lower energy state and the radiation energy density. When we remove that proportionality constant, we get this constant B12. So B12 is called as the Einstein's coefficient of absorption, and it gives the probability of the absorption or the probability of the induced transition from the level 1 to the level 2. Similarly, we can define the Einstein coefficient for the spontaneous emission. So what happens in the spontaneous emission? The atom which is already in the excited state drop down to the lower energy state or on the ground state by emitting one photon. So the rate of spontaneous emission from the level E2 to E1, it will depend upon the number of atoms which are present in this excited state, and it will be independent of the energy density. So RSP, meaning the rate of spontaneous emission, is proportional to N2, and when we remove that proportionality remove that proportion, we get this constant A21. It is known as Einstein's coefficient of spontaneous emission. Again, it gives the probability of the spontaneous transition from the level 2 to level 1. Third process is stimulated emission. So what happens in the stimulated emission? We have already atoms which are present in this excited state. They will interact with the incident photon and will drop down to the lower energy state. So the rate of stimulated emission, it will depend upon the number of atoms which are present in the upper energy level as well as on the energy density of the radiation, because the radiation is being impended on the system. So RST, that is the rate of stimulated emission, is proportional to N2 and U function of nu. Again, when we remove that proportionality, we put this constant B21. This is known as Einstein's coefficient of stimulated emission of radiation. So these are the three processes and their Einstein coefficients. So whenever a photon interact with the system, whenever the photon is incidented on a material, these three processes happens. It is not like that only absorption will occur or a spontaneous emission will occur. These three processes occur simultaneously. Under the steady state condition, absorption and emission processes balance each other. So rate of absorption is equal to the rate of emission. So now here we have one absorption and two emissions. So rate of absorption will be equal to the rate of spontaneous emission plus the rate of stimulated emission. And I have put it these values which we have earlier calculated here. So now we will move to the next section. That is a component of lasers. But before discussing the components of the laser, we need to understand certain definition which are required for the laser action. So as I have told earlier that whenever the photons are incidented on a material, three kind of process can occur. Whenever the photon is incidented on a material, under the normal condition, large number of atoms are present in the ground state. So when the photon is incidented, then it is more likely to get absorbed in the system. The chances of absorption are more as compared to that of the stimulated emission. The atom will absorb that light and will move to the upper level, rather than that excited atom will interact with that photon and will come to the ground state. So it means that the absorption process will always dominate upon the stimulated emission process. For the laser, I should make it, I am saying it once again, that in the laser process, what we require is that the stimulated emission should occur largely as compared to the absorption and spontaneous emission. Only then we will be able to get our light signal amplified. Right, so stimulated emission should be more as compared to the absorption and the spontaneous emission. So and for getting more stimulated emission, the condition is that we should have the more number of atoms in the excited states, so that the incident photon can interact, so that the atom can interact with the incident photon and come to the ground state emitting two photons. Right. So normally in the ground state, the number of atoms are more as compared to the excited state. But we have in order to get the stimulated emission, the majority of the atom should be on the higher energy levels. Under the normal and thermal equilibrium condition, which is the population ratio, which is given by the Boltzmann distribution law, it tells us that N1 will always be greater than N2. But to achieve the high percentage of stimulated emission, we want N2 greater than N1. So this is a non-equilibrium condition. That is why it is called as an inverted state non-equilibrium condition. This situation we have to obtain in order to get the high percentage of stimulated emission. So how we obtain this situation? This situation can be obtained by supplying some external energy, so that we have a large number of atoms in the higher state as compared to the lower state. And this state is called as a population inversion. So what is population inversion? It is a non-equilibrium condition of the material in which the population of the upper energy level momentarily exceeds the population of the lower energy levels. Meaning we have to make this situation, that is N2 should be much greater than N1, because we have to supply the energy to obtain this condition, and this is a non-equilibrium condition, right? So the and the method which we are using to get this population inversion condition, those methods are called as the pumping methods or pumping techniques, which will be discussed in the later sections. So first important thing which we need to get the high percentage of stimulated emission which is required for the laser action is the population inversion. Second thing is a metastable state. Now, as we have seen in the spontaneous emission, that the atom which is excited to the higher energy level, the atom which has gone from the ground state to the excited energy state, it do not stay here for the longer time. It within 10 to the power minus 8 or 10 to the power minus 9 seconds, it comes back to the ground state by emitting the photon, right? Because by the spontaneous emission. But in order to get the high value, in order to get the high percentage of stimulated emission, the requirement is that the atom should remain in the excited state for a appreciable amount of time, so that the stimulated emission can take place. Because for laser, I'm again saying this, for the laser the primary condition is a stimulated emission. Only by the stimulation emission process we will be able to get the light amplified. So generally the excited states have very less lifetime. So one such state which has a comparatively longer lifetime as compared to that of the ordinary excited state, such states are called as the metastable states. So in the metastable states are the states in which the time is of the order of 10 raised to power minus 6 to 10 raised to power minus 3, which is much larger as compared to the time in the ordinary energy states. So whenever so if the atom is staying in the in excited energy level for a appreciable amount of time, only then it will be possible to create or to establish the state of the population inversion. Otherwise it will be impossible. Meaning you are pumping the atoms to the higher energy state, but they are immediately coming back to the ground state. Then what will be then the point or idea of getting it pumped to the higher energy levels? So if it will be meaningful only if the atoms are staying in this state for the appreciable amount of time. That is why the metastable that is the importance of the metastable states. Third is a confining the radiation within the medium. Now, as I have told that in the stimulated emission should dominate over the absorption and spontaneous emission. Now, for the stimulated emission to dominate over the spontaneous emission, a high radiation density is required. Radiation density I have already defined previously. The energy, so high energy density, high radiation density is required to be present in the active medium for stimulated emission to dominate over the spontaneous emission. And this high energy density situation or this condition can be achieved if we place the laser medium between the two optically parallel mirrors such that the photons can reflect back and forth from those mirror, and the photon density can build up to a very high value, and the stimulated absorption can dominate over the spontaneous emission. Such an arrangement in which the material medium, a laser medium, is placed between two optically plane mirrors is called as the optical resonant cavity or optical resonator. So now we'll move to the next topic, that is components of laser. Now, as we have seen the three basic requirements for the light amplification or for the stimulated emission to take place. One is population inversion, next is a metastable state, and third is confining the radiation within this medium. And for that confinement, that arrangement which we make is called as the optical resonant cavity or optical resonator. So component of the laser there are different type of the laser, but the basic or main component of the laser are the active medium, the pumping agent, and the optical resonator. Now this is a schematic how these active medium is placed. This is the active medium. This is the pumping agent which is supplying the energy to the active medium, and active medium is placed between these two mirrors. One mirror is completely polished, 100% reflecting, and the other mirror is partially reflecting. It is 90% reflecting and 10% transmitting. So these are, and this setup constitutes the components of relay. So first of all, talking about the active medium. So what is an active medium? It is a medium. Now, active medium can be any material medium, but as in the material medium, we have a number of energy levels, we have number of atoms, and all the atoms are not suitable for the establishment of the condition of population inversion. Only there are certain kind of atoms which can cause the amplification of the light. Means there are only certain kind of atoms which can establish and maintain the condition of the population inversion. So those atoms are particularly useful for the laser action. So these kind of atoms in the material which are helpful in the population inversion and the light amplification, these type of ions or atom, they are called as a active center. They are called as a active centers, and the medium which host all these active centers, that is called as a active medium. So we can define as the medium. It can be any medium, solid, liquid, gas. So it is a medium which when excited, it reaches the state of the population inversion. The material should be such that it should reach the state of the population inversion, and it should promote the stimulated emission, which will ultimately lead to the light amplification. The second component is pumping. So pumping, it is required for the population inversion, which we have previously discussed. So what is pumping? It is basically the process of supplying the energy to the medium so that it can achieve the state of the population inversion. So pumping is a process simply which supplies the energy to the active centers in the medium. There are many techniques which are used, which can be used in the pumping, such as the different kind of pumping depending upon the laser, optical pumping, electrical discharge, and direct conversion. The third part, the third component of the laser is optical resonant cavity. So this is required for high radiation energy density. So what is the meaning of that? So optical cavity, we have two mirrors. One is 100% reflecting and another is 90% reflecting. So what happens? The photons are generated in the active medium and they reflect back and forth between these two mirrors, and they get multiplied in the process whenever they will pass through this medium. So in the absence of the resonate, this setup is called as resonator cavity or optical resonator. If it will not be present, if these mirrors are not present, then there will be no amplification of the light, because amplification of the light is obtained because the atoms are getting reflected back and forth between these mirrors, which is your optical which is the resonator cavity. So without the presence of the resonator cavity, there will be no amplification of the light. So now talking about the laser action, how the laser light we can obtain from this setup. So again, this is a setup. We have this active medium. These are the two mirrors. One is fully reflecting and another is partially reflecting. These arrows are showing the pumping energy which is being provided to this active medium. So initially, the atoms are in the ground state. The active centers, they are in the ground state. Whenever the pumping energy is supplied to the active medium, that atoms will gain the energy and will move to the excited energy states. In this way, a condition of population inversion will be obtained. So firstly, whenever pumping is done, whenever the pumping energy is provided to the active medium, to the active centers in the medium, we are getting the condition of the population inversion. So what is the meaning of population inversion? That we have the large number of atoms at the higher energy level as compared to the lower energy level. Now, what happens after that? Whenever the condition of population inversion is established, the atoms, one of the atom from the excited upper energy level will come down to the lower energy levels on its own by spontaneous emission. And in this process, one photon will be emitted. Now, that one photon, which is obtained from the spontaneous emission, that will trigger the process of stimulated emission. That photon will force the other atoms which are in the excited state to come to the ground state. And in this process, and in this way, the stimulated emission process starts. So whenever the stimulated emission process start, one photon will lead to the other atoms to come to the ground state, and in this process, more number of photons are emitted. So those photons which are traveling along the axis, which are traveling in this horizontal axis, they will be only amplified. The photons which will be moving in the other direction, they will be lost. They will not get multiplied, they will not get amplified, they will pass through the sides of the medium and they will be lost forever. Only those photons which are traveling along this axis, they will be amplified, right? So now as the photons are generated here, now they will come to this side. From this mirror it will be reflected. Again it will pass through this medium. Again it will force more atoms to come to the ground state, and in return more photons are emitted. So in this way, again it will be reflected back and forth between these mirror, and stimulated emission process, it increases sharply. And with a sharp increase in the stimulated emission process, there is a amplification of light. So this is a situation in which we are now getting large number of photon and stimulated emission process, and we are getting the amplification of the light. So at each reflection at the now these two mirrors are such that this mirror, on this front end mirror, it can transmit some amount of light from here. So whenever this amplification of light is balanced by the losses in the cavity, the small radiation will be emitted from this mirror, which is partially transmitting. So at the so each reflection at the front end mirror, light is partially transmitted. So we are getting a strong, steady laser beam at the front end of the mirror. So this is how we obtain the laser light by using this process of stimulated emission. So now the types of the laser, depending upon the, if we can categorize laser on the different basis. If we categorize them in on the basis of the medium which is used, they can be categorized as solid state laser, gas laser, liquid laser, semiconductor laser. Some of the important lasers are ruby laser, in which this is a solid state laser in which we use a ruby crystal doped with the chromium ion. and helium neon laser, anti-ag laser, carbon dioxide laser, semiconductor laser, etc. So we can discuss these laser in some other time, in some other live lecture. So these are the characteristics of the laser beam. Laser beams are highly directional as compared to the ordinary light sources. In the ordinary light sources, lights travel in every direction, in each and every direction in ordinary sources. But in the case of the laser, as we have seen, that the photons which are getting multiplied, or which we are getting as a laser beam, are only photon which are traveling along the horizontal axis. So the laser beam is highly directional. It travels in that direction. It offers a very high directionality. Second important property is a negligible divergence. It diverges very little as compared to the ordinary sources. Ordinary sources are, suppose we have a point source. The light from that point source will go in every direction. But in the case of the laser, it diverges very little. For example, the diameter of the laser beam increases only 1 millimeter if it travels a distance of 1 meter. So from this we can get the idea that how much divergence, how much the light diverges as it travels through the medium. Because of this property, it also has a high intensity. The laser light is highly intense, so it is always advisable to not directly look into the laser beam, because it is a light of a very high intensity. As all the next property is a high degree of coherence. Now as the photons which are generated in the stimulated emission process, which is the basis of the laser, all those photons, they are in phase with each other. So the light which we get as a result in the form of the laser, as a result of the stimulated emission, all those photons, they have a constant phase difference between them. So they can offer a very high degree of coherence as compared to the ordinary light sources. Two independent sources can't be coherent because they emit the light in the different directions. Also, there is no phase correlation between the light emitted from those sources. Contrary to that, laser sources, they offer a very high degree of coherence. Next is a high monochromaticity. Laser light are highly monochromatic. The word monochromatic means that the light of single color, or the light of single wavelength or single frequency. So laser light also offer a very high degree of monochromaticity. So due to these characteristics of the laser, it has found many applications in different fields. So these are some book references for the further studies on lasers. Thank you.